Hello, good morning all. This is Dr. Abdul Pasha, working as Assistant Professor, Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. So, we are in the course of Power System Operation and Control. Here, the topic is Hydro Range Scheduling Process. So, what is hydro range scheduling process? That we are going to discuss. The hydro range scheduling is involved in majorly two cases. The first case is a long range hydro scheduling process. Second one is short range hydro scheduling process. So, what is this long range hydro scheduling process? So, here long range hydro scheduling process means the long range hydro scheduling problem involves the long range forecasting of water that will be available, and the scheduling of reservoir water is going to be releases. That is a drawdown or drawback for a given interval of time that depends upon the reservoir capacities. So, long range hydro scheduling process means this is the forecasting of availability of the water and the scheduling of the reservoir water releases that will be drawdown for an interval of time that depends upon the reservoir capacities. So, based on the capacities of the reservoirs, the availability of the flow must be considered. So, this is the releasing of the water level from the reservoir or dam. So, this may going to include in the system to the extent level of the water. So, during which the power generation is going to be takes place. Next one is short range hydro scheduling. What is short range hydro scheduling means? This short range hydro scheduling process takes place from 1 day to 1 week period. This is the period of instance the short range hydro scheduling process is going to be taken place. So it involves the hour by hour scheduling of all the generation on a system to achieve minimum production cost. To achieve minimum production cost, we are using the short range hydro scheduling process for the given time period. So in such a scheduling problem, the load, hydraulic inflows and unit availabilities are assumed to be known. So what are the conditions to make this means? We should know hydraulic inflows, unit availabilities, that parameters we must know. Set of starting conditions like reservoir levels are given and the optimal hourly schedule that minimizes the desired objective while meeting hydraulic and electric system constraints is going to be sorted out. So these are the main constraints we should consider, like load assumption, hydraulic inflows, and unit availabilities. Unit availabilities. So these are the parameters we must consider while making short range hydro scheduling process. So coming to this, load schedules in electrical systems are key to efficiency and stability case. So they matter from small bulbs to huge wind turbine generators. This is the smallest load case to the huge wind turbine generators case. These are supposed to be scheduled. Coming to this, load planning and task scheduling, they play a vital role. So they are not just fancy words but core practices in energy projects. These are going to be considered. So major energy projects like ABB, Siemens. So these are the projects they will consider these load planning according to the grid connectivity and task maintenance like task scheduling process. These are going to be considered. So fancy energy with 2 decades of expertise highlights low precise resource allocation. That means this leads to project success and the sustainability of the system. So let's shed light on this critical topic, that is hydro scheduling. Thus we will discuss. So adapting backward or forward scheduling brings many benefits. So that means it reduces unused stock and simplifies scheduled tasks. So boosting overall efficiency and precise timing is crucial, especially in places where budgeting is done in rupees. So this reflects the needs of financial wisdom in today's projects majorly. So such scheduling methods ensures projects finishes the particular given time. So with this, they also helps to create a greener idea in that we will make the thanks to fancy energies renewable energy efforts. These efforts makes the system to operate under stable conditions. So there is a simple two-unit system. We are making this hydro scheduling process with their fuel costs of F1 and F2. So this simple two-unit system including two very similar units that have the following input-output cost functions and incremental cost functions like F1 and F2. So F1 is where 8P1 plus 0.024P1 square plus 80. F2 is 8.2 P2 plus 0.025 P2 square plus 82. So here we need to calculate for two incremental fuel costs of P1 and P2 suggested values. So these values once we know, if you substitute here, then we can easily or automatically calculate the incremental fuel costs of the two units, that is F1 and F2. So usually we may represent it as a minimal F value as summation I equals to 1 to n Fi of Pi. So this function will be represented as I equals to 1 to n Fi of Pi. And this may be treated as a difference of these two parameters, that is Pi minus Pd, which is about summation I equals to 1 to n Pi minus Pd, where this difference is treated as a difference of this function Fi of Pi case. So this may existing from minimal to maximum, that is Pi minimum less than or equals to Pi, which is less than or equals to P max, where F is the operating cost, N is the number of generating units, Pi is the power output of the ith generating unit, and Fi of Pi is the individual fuel cost function of ith generating unit. So PD is the demand, here load demand. According to the load demand we will treat, and Pi minimum is the ith generating units minimum. So these are the variables we must consider while defining the cost function of the generator case. So the variables are existing from I equals to 1, 2, 3, so on up to n number it is existing. So coming to the maximum power case, that is Pi max is the ith generating units maximum output. So fuel cost function or input output characteristics of the generator may be obtained from design calculations or from heat rate tests. So the fuel cost function of generator that usually used in power system operation and control problem is represented with a second order polynomial, that is Fi of Pi equals to Ai plus Bi Pi plus Ci Pi square. So where Ai, Bi, Ci are non-negative constants. That means for ith generating unit, some generators like large steam turbine generators, however, having the input output characteristics. So which is not always smooth, but they have large steam turbine generators will have a number of steam admission valves, so that are opened in sequence to obtain ever increasing output of the unit case. So this kind of units input output curves are going to be represented, that we already seen. So the fuel cost function of this kind of unit can be expressed as Fi of Pi equals to Ai plus Bi Pi plus Ci Pi square plus Ei of sine of Fi of Pi minimum minus Pi. So this is the resultant expression which we will conclude for fuel cost function as a kind of unit which will be expressed. So the dynamic economic dispatch is one of the main functions of the power system operation and control. So it is a method to schedule the online generator outputs with the predicted load demands over a certain period of the time so as to operate an electrical power system most economically. So while the system is operating within the security limits, the problem is a dynamic optimization. That means which will be taking into account to the constraints imposed on the system. So that will be reflected to the generator ramping to the specified rating limits. So the dynamic economic dispatch is not only the most accurate formulation of the economic dispatch problem, but also the most difficult to solve because of its large dimensionality. So due to its large dimensionality, it will be treated as most significant thing. So this dynamic economic dispatch will accurately formulating the resultants to the limited extent. So these constraints imposed on the system, and due to this problem, dynamic optimization is taken into consideration. So this will be for a period of time, and it will be predicted for suitable loads. This is predicted for suitable loads. So it is the method we will make the scheduling of this hydro terminal case with the generators that may be depends upon the number of units. Number of units which will be treated as one of the cost functions. Which will be treated as one of the cost functions in the hydro power system network. So here the problem can be mathematically formulated as minimal of the function as summation small t equals to 1 to capital T summation I equals to 1 to n fi t of PAT. So this is going to be taken place in between the time periods 1, 2, 3 up to so on capital T. So which is subjected to power balance constraint, that is summation I equals to 1 to n PIT minus PD equals to 0, that is I equals to 1, 2, 3 up to so on n. So unit capacity constraints are going to be considered, that is PIT minimal less than or equals to PIT less than or equals to PIT max. So these are also rotated in the variable sequence of 1, 2, 3, 4 up to so on n number. Here time factor also considered, that is 1, 2, 3, 4, 5 up to so on capital T. These are going to be existing. Now, when it is the case of ramp rate constraints, then it may be treated as PIT minus PI of T minus 1 less than or equals to URI. So, PI of T minus 1 minus PIT less than or equals to DRI, where I equals to 1, 2, 3 up to so on n, T equals to 1, comma 2, comma 3 up to so on capital T. So, this is another expression which is going to reflect the ramp rate constraint, and unit capacity also considered, but according to the power balance expression only we will decide to make the meeting of the load requirement or meeting of the load demands in such a case. Since dynamic economic dispatch was introduced to the several optimization methods, and they have been used to solve this problem in such a case. So this power balancing equation makes the system constraints to get the suitable resultants to the extent case. So here one of the problem is given based on the economic dispatch of the power system network in hydro range scheduling process. That is, it is considered with a 3 generator systems. So here the system is developed with 3 generators named as generator 1, generator 2, generator. Here 3 generators are named with H1, that is 510 plus 7.21 P1 plus 0.0142 P1 square, which is MBTU per hour. So here 3 generators are tied together, and H2 has 310 plus 7.85 P2 plus 0.0194 P2 square, which is also in MBTU per hour. This is the second case. Coming to the third case, that is reflected as H3, that is 78 plus 7.97 P3 plus 0.0048 P3 square in MBTU per hour. So like that, three combinations are existing as H1, H2 and H3. So these are the three combinations which are existing here. So with this, we are going to calculate the major economic dispatch problem in the power system network. So here fuel costs are mentioned. That is for unit 1, the fuel cost is 1.1 rupee per MBTU, which is lies in between 150 less than or equals to P1 less than or equals to 600. And similarly, unit 2, fuel cost existing is 1 rupee per MBTU, that is 100 less than or equals to P1 less than or equals to 400. And unit 3 also existing as fuel cost equals to 1 rupee per MBTU, that is 50 less than or equals to P1 less than or equals to 200. So these are the ranges of the various power demands existing for various units, and these are treated as fuel costs for respective units like unit 1, unit 2 and unit 3. So for example, if it is existing as F1 fuel cost 1, then it is multiplied with H1 into fuel cost 1. That is 510 plus 7.2 P1 plus 0.0014 P1 square into 1.1. And it may be written as 561 plus 7.92 P1 plus 0.001562 P1 square. This is treated as equation 1. Similarly, fuel cost 2 for second unit, it may be written as F2, that is H2 into fuel cost 2. So here H2 value is about 310 into fuel cost, that is 7.85 P2 plus 0.00194 P2 square. Similarly, F3 existing as H3 into fuel cost 3, that is F3 equals to 78 plus 7.97 P3 plus 0.00482 P3 square. This is the fuel cost 3. Now making total operating load as a PD, that is equivalent to 850 megawatts. This is equivalent to total 850 megawatts, and this may be written as sum of the three loads combination P1 plus P2 plus P3. This is the three units combination, that is P1 plus P2 plus P3. So while solving this problem, we need to go for making lambda iteration method, that is df1 by dp1 equals to df2 by dp2 equals to df3 by dp3, which is equivalent to lambda case. So for optimal generation scheduling, it is existing as df1 by dp1 equals to 7.92 plus 0.003124 P1, which is equals to lambda. And df2 by dp2 is 7.85 plus 0.00388 P2, which is equivalent to lambda case. And also df3 by dp3 as 7.97 plus 0.0096 P3, which is equivalent to lambda case, where lambda is the iteration method constant. This is also called as Lagrangian's quotient. Lagrangian's quotient. Lambda is Lagrangian's quotient. So now applying the given variables in respective P1, P2, P3 cases, P1 is lambda minus 7.92 by 0.003124. P2 has lambda minus 7.85 by 0.00388. P3 has lambda minus 7.97 by 0.00964. So this total combination existing as one of the three combination sets with Lagrange's coefficient lambda. So substituting for P1, P2, P3, P4 combinations, in the given expression, then we may obtain. That means here the P1, P2, P3 combination is existing with 850 megawatts. So here we need to substitute this. Actually, we have P1 plus P2 plus P3, which is equals to 850 megawatts. So substitute for P1, substitute for P2, substitute for P3. So where P1 is a lambda minus 7.92 by 0.00312 plus P2 is lambda minus 7.85 by 0.00388 plus P3 is lambda minus 7.97 by 0.0096. So when you all equate these combinations to 850 megawatts, then we are going to obtain the resultant. So all these lambda combinations, we will frame a simple expression by taking the LCM of one of the set, any one of the set combination. After solving, we have to add this combination here, and here you may get the expression in lambda case 681. That is, this is obtained when you are adding these three sets as lambda minus 7.92 by 0.003124 plus lambda minus 7.85 by 0.00388 plus lambda minus 7.97 by 0.00964, which is equals to 850 Ks. And equating to this 681.57 lambda minus 5385.6706, which is equals to 850. So the final combination is in terms of lambda as 850 plus 5385.6706 by 681.57. So now calculate for lambda. That means adding these two combinations. 850 plus 5385.6706 by 681.57. This numerator and denominator combination will resultantly gives a lambda values of 9.148 rupees per megawatt hour. So this you are going to get as one of the lambda constant, 9.148 rupees per megawatt hour. So P1 combination as 9.148. Here all the cases we need to substitute lambda in P1, in P2, in P3. So this set may be represented here. This is the value of lambda 9.148. This is the value of lambda also 9.148. This is the value of lambda also, that is 9.148. So substituting for this, 9.148 minus 7.92 by 0.003124. So subtract these two combinations and this numerator relation by denominator relation gives 393.08 megawatts. And similarly for P2, 9.148 minus 7.85 by 0.00388, which gives 334.5 megawatts. And P3 also gives 9.148 minus 7.97 by 0.0096. And this resultant gives 122.2 megawatts. So with this we may obtain P1 as 393.08 megawatts. Similarly, P2 gives 334.5 megawatts. Similarly, P3 gives 122.2 megawatts. So summing all these combinations, that is P1 plus P2 plus P3. That is P1 is about 393.08 plus P2 is 334.5 megawatts plus P3 is 122.2 megawatts. Now add all these 393.08, next 334.0550 megawatts plus 122.20 megawatts. So adding this 8, 7, 3 plus 4, 7 plus 2, 9, 12, 9 plus 3, 12 plus 2, 14. So here 6, 7, 8. 849.78 megawatts. So this is the resultant we obtained when we calculated for P1, P2, P3 combination. That means this is the total summation of this case. So actually it is given with a total of about 850 megawatts. What we obtained is 849.78. So this is nearest to that 850 megawatts. So like that we will obtain the different combinations, and by that if you are summing all these P1, P2, P3 combinations, you may get the final value of 850 megawatts. So suppose the price of first unit, that is unit 1, is decreased to the extent of zero point 0.9 rupees per megawatt hour, and you need to calculate the optimum schedule. Then this will be followed like this. The fuel cost function of unit 1 becomes F1 of P1. It is given with F1 of P1 equals to 510 plus 7.2 P1 plus 0.00142 P1 square, which is multiplied with 0.9. Why? Because the price of unit 1 is decreasing to 0.9 rupees per megawatt. That's why we are going to multiply here. Similarly, this F1 of P1 is followed with 459 plus 6.48 P1 plus 0.0127 P1 square. So when you're making to this, then you are going to multiply it with all these combinations. That means 0.9 into 510, which gives 459, and 0.9 into 6.48, which gives this is about 7.2 P1. So 7.2, 0.9 into 7.2, which gives a value of 6.48. And similarly 0.9 into 0.001278 combination. So here this value is multiplying means which is done with the 0.00142. This is only giving 0.001278. So these are the values we obtain when we make. This is about 459. This is about 6.48, and this is about 0.00127. So these are the resultants we will have. Now making for this one as a df1 by dp1, which is 6.48 plus 0.00256 p, which is equals to lambda quotient. That is P1 equals to lambda minus 6.48 by 0.00256 combination. So this is we obtained from this condition. From this condition, we are getting this P1 value as lambda minus 6.48 by 0.00256. And P2 as lambda minus 7.85 by 0.00388 combination. And P3 has lambda minus 7.97 by 0.0096. So these are the three sets of the combinations P1, P2, P3 we may obtain with these values. So if you simplify these combinations by adding all the P1, P2, P3 sets, then you are going to obtain one of the lambda value. So that we will see now here. Substitute for P1, P2, P3 in equality constraint. That means what we have, P1 plus P2 plus P3, which is equivalent to PD, that is equivalent to 850. Here substitute for P1 value, substitute for P2 value, substitute for P3 value. So P1 is about lambda minus 6.48 by 0.00256. And P2 is lambda minus 7.85 by 0.00388 plus lambda minus 7.97 by 0.00964 combination is P3. This is P3, this is P2, this is P1. So with this all combination you are getting total value of 850. So this may equivalent to 752.1 lambda minus 5381.21, which gives a value of total 850. So this expression can be simplified as equating to the lambda case. Then it becomes 850 plus 5381.21 by, this will comes to denominator case, that is 752.1, that is 8.285. So now lambda equals to 8.285 rupees per megawatt. So adding these two combinations, 850 plus 5381.21 by 752.1, that is 752.1. So you add this and divide with the 752.1, then you may get 8.285 in rupees per megawatt. Now, schedule of the units may be considered as substituting the values of the lambda here. So, we are getting the lambda as 8.285. That value we need to substitute here. Lambda is which is about to 8.285. 8.285. This we need to substitute here. For example, if it is the case of P1, P1 is 8.285 minus 6.48 divided by 0.00256. So subtract these combination and divide it with 0.00256. Then we are going to obtain a value of 705 megawatts. Similarly, we should make sure for P2 lambda minus 7.85 by 0.00388 combination. So here lambda value we have, that is about 8.285 divided minus 7.85 divided by 0.00388. Subtracting from 8 to 7, and you are going to get P2 is about 112.1 megawatts. Similarly, go with the P3 case, that is lambda minus 7.97 by 0.0096, where we obtained the lambda as 8.285 minus 7.97 divided by 0.0096. So this is the P3 combination. Subtract from here and you may obtain with the value 32.67 megawatts. So this is the result you obtained for P3, and P1 is about 705 megawatts, P2 is 112.1 megawatts, P3 is 32.67 megawatts. So when you add all these combinations, that means what it is, 705 plus 112.1 plus 32.67. So just add this combination, then it may be reflected to 850 megawatts, nearest to the 850 megawatts. And both the units P1 and P2 are found to violate the inequality constraints. That means P1 is about 600 megawatts, P3 is 50 megawatts. So P2 is 850 minus 650 plus 50. So what is happening here? This is the total load, that is P1 plus P2 plus P3 combination, and this is adding to 650. That means 650 plus 50 combination. Then so you are getting 200 megawatts. So 200 megawatts means this 600, this 250. Total how much? 600 plus 200, 800 plus 50, 850 megawatts. So P1 is 600 megawatts, P2 is 200 megawatts, P3 is 50 megawatts. Like that we can calculate these three variables like P1, P2, P3 combinations. And if you make it for dF1 by dP1, that means incremental fuel costs at a rate of P1 of about 600, then it is 6.48 plus 0.00256 multiplied with 600. So we know that this 600 combination is nothing but P1. So from this relation, 6.48 plus 0.00256 P1. With this, we are going to get a value of df1 by dp1 at the rate of p1 600. So that 600 we substituted. So adding these two, then you are getting 8.016 rupees per megawatt. Similarly, df3 by dp3, that is p3 is 50, then it is going to be added like this 7.97 plus 0.00964 into 50 case. So if you add this, then you are going to get 8.452 rupees per megawatt hour. So this is about df1 by dp1, incremental fuel cost 1, and this is incremental fuel cost 2. And the lambda nu becomes dft by dp2, that is 7.85 plus 0.00388 multiplied with 200. So this combination is multiplying here 0.00388 multiplied with 200. The resultant is added to the 7.85 case. Then you are getting the new lambda value as 8.626 rupees per megawatt. This is the value of new lambda. So for unit 1, unit 3, the following conditions need to be satisfied for obtaining various lambda values. That is the one of the Lagrange's coefficient. That was taken place in between df1 by dp1 less than or equals to lambda nu, as p1 is p1 max, and df3 by dp3 less than or equals to lambda nu, as p3 is p3. These are the two conditions we will see here. And the first is satisfied, but the second condition, that is df3 by dp3 is 8.452 less than new value of the lambda. Therefore, it cannot be fixed at the lower limit. And now let us fix it for P1 about 600 megawatts. Then this will be the economic dispatch for units 2 and 3. Then PD nu equals to PD minus P1. So we have total load, that is 850. We have P1, that is 600. 850 minus 600 gives total value about 250 megawatts. Here P2 is lambda minus 7.85 by 0.00388. Substitute that lambda value here and equating to that in the same aspect of P3, lambda minus 7.97 by 0.00964. Then P2 plus P3 is PD nu, that is lambda minus 7.85 by 0.00388 plus lambda minus 7.97 by 0.00964, that is equating to 250 megawatts. Now, making the LCM of these coefficients, then the expression we are getting is in terms of the lambda. So that lambda expression may 361.46 lambda minus 2849.95, which is equals to 250. So simplifying this, that means 361.46 lambda is equals to 250. This will comes to this side. That means adding to this 2849.9. So these two combinations are added, 2849.95 and 250. So when you add this may about 5, 9, and here it is about 9, again 9, 10. This will be like this. So this is, we are getting the case, but in terms of the rupees per megawatt hour, the lambda value becomes 8.576. So this much of value we are getting as a new lambda value. So this is the new Lagrange's coefficient, that is we are going to get 8.576 rupees per megawatt hour. So this value may be obtained or treated as newest value of the lambda case, that may be treated here. The first is satisfied, but the second condition is treated in the range of 8.452 less than newer value of the lambda case. This lambda value will be existing in the second attempt of the hydro range scheduling process. So like that we can calculate the lambda values that should be ranging from in between P1, P2, P3 respectively. So with this the Lagrange's quotient may be obtained suitably. So these are some of the textbooks whatever I referred as electrical for you, and some of the contents from video lectures, some of the website resources, some of the from free engineering textbooks. So like that hydro range scheduling plays a key role in the power system operation and control. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.